All of what you see in the blue box right in here, these things right here, should all be familiar to you. We've talked about reciprocal trig functions. Now, name the reciprocal of a simple fraction like 2/3. Can you name the reciprocal? 3/2, right? What about 1/2? Is that the same thing? Is the reciprocal of 2/3 1/2? Okay, maybe I should write that down. So you said that, that's why I didn't. So 2/3, you said the reciprocal was 3/2. My question, is this the same thing as 1/2? Are those two things the same? Yes, you need to understand that. So for instance, if I say, what's the reciprocal of 5? You should be able to tell me 1/5. That's why all of these fundamental identities should make sense to you already. Cosecant goes with sine. Secant goes with cosine. Tangent goes with cotangent. All that should be stuff that you already know. That shouldn't be anything unusual to you. Now, can you name the number in the universe which we call the identity for multiplication? Can you name the number in the universe which we call the identity for multiplication? 1. Why do we call it the identity? Right, because when you multiply by the number 1, you get the same identity. That number hasn't changed. What about for adding? What is the identity for addition? 0. These are called identities. Now, if something is an identity, you can replace it with its equal. What do we typically call that? Replacing something with its equal. Substitution. Folks, you're going to have to do a lot of substitution. So, sorry, had to hyphenate, ran out of room. You better get very used to doing substitution. The quotient identities that they list right there. Tangent. Tangent, we should know that's y over x, right? That's the slope of the line. Well, if y is the sine and x is the cosine, then we should be able to write that as sine over cosine, which makes sense. And then cotangent would be the reciprocal of that, cosine over sine. Those are basic facts that you need to know. I should have put this at the beginning. The How to Win the All Valley Karate Tournament. That's from Karate Kid. All the things he was asked to learn. The last one is at the end. Why is this in here? Okay, that is not what I wanted. Let me pause this. Okay. The point that I'm going to pick on the circle, yes, it's based at a 30-degree angle, but that's not the important part here. It could be any point on the circle, and I'm going to draw a triangle, a right triangle. Not a very good one, but... And folks, I'm not really... yeah, I know I chose a 30-degree angle, but I don't really care. I'm not interested in you telling me it's 1/2 and radical 3/2, that kind of stuff. I am interested in understanding which side of this triangle, if I could actually do what I'm wanting to do, which side of this triangle would you call x, and which side would you call y? Which side would you call x? X is your horizontal on the bottom, and y would be your vertical on the right side. Okay. And can you tell me, from your vast experience, what x squared plus y squared equals? 1 squared, also known on the street as 1. But you're right, it is 1 squared. What is the cosine of theta? The adjacent side divided by the hypotenuse, also known on the street as x. And the sine of theta, opposite over hypotenuse. Y over 1, also known on the street as y. So what could you substitute for x and what could you substitute for y? Cosine theta, yeah, we could substitute that for x. What about for y? Sine theta, right? Now, in a lot of books, you will see it written like this: cosine squared theta plus sine squared theta equals 1. All they're trying to do by putting that little square next to the cosine or the sine is indicate that they're trying to square the cosine, not the angle theta. Some people forget these, will forget these parentheses like that, and so people look at it and say, oh, they're squaring the angle theta. No, we're not squaring the angle theta. We're squaring the cosine of theta. But those notations mean exactly the same thing. However, you will see it written a lot of times the second way there at the bottom of the screen. This is obviously called the Pythagorean identity. Now, for those of you wondering, will we get all of these identities on a formula sheet for the test? What do you think? Yes, we will. You need to know how to use them, but you will get them. Sorry. I need you to get very comfortable with what you see in that blue box. Suppose you saw that in the blue box on a homework problem or a quiz or a test. What would you substitute for what's in the blue box? What could you substitute for the stuff in the blue box? One. It says that the blue box is equal to 1. I'm trying to make a big point here. In the world of trig, when you see cosine squared theta and sine squared theta, a lot of crap is disappearing. That's a good thing, isn't it? You can replace all of that with the number 1. Ooh, lots of stuff is going your way. It's nice in these trig identity sections when you can see things cancel out. Some things add up to 0. We like that too. When things add up to 0, oh man, that's nice. You can just get rid of stuff. When you see this, you better be replacing it every single time with that number 1. That's why we call these identities, because they're things that we can substitute for something else. Now, for those of you who printed out these notes, these should actually say squared, cosine squared theta or sine squared theta. So, let's take our Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. And let's divide everything by cosine squared theta. What do you get here? What's cosine squared theta over cosine squared theta? 1 plus, what's this thing? Woo, nice. Tangent squared theta. right? That's that sine over cosine. What's on the other side? What's 1 over cosine squared theta? Ah, secant squared theta. We're using our identities. Yeah. We used a little bit of algebra, right? Anything divided by itself is 1. But we are using our identities. We're using our identities to do substitution. Is this one going to show up on my answer sheet or my formula sheet for the test? Yes, it is. So we had, hold on, I'll come back to it. So we definitely are getting that one. But we're also getting this one. What happens if we take cosine squared theta plus sine squared theta equals 1, and we divide all of these by sine squared theta? Oops, that should not be. What happens? Cotangent squared theta plus 1 equals cosecant squared theta. And yes, you'll get that formula too. What you won't get is this. What is cotangent squared theta equal to? If I were you, I'd use the one right above it to help you. See, you just use, sorry, I can't spell. I've got to go back, try that again. You just used your algebraic skills to subtract 1 on both sides of that. So if you're working on a homework question and you see this thing right here, you can substitute that with cotangent squared theta because they're equal. What about up here? What if I said, what is tangent squared theta equal to? Secant squared theta minus 1. Yep, all you're doing is manipulating the 1, subtracting it to the other side. Before we go too much farther, I want to ask you, lots of stuff that's happening in this chapter is going to be based on whether you understand Algebra 2. So for instance, do you know how to factor? Do you know how to find common denominators with fractions? Oh, yeah, I know, that goes back to junior high. Scroll down like this stuff. Like that? Okay, sure. Do you know how to use the distributive property? Do you know how to use the distributive property backwards? We call it factoring out a greatest common factor. Those kind of things. That's all Algebra 2 stuff, and you need to know how to do it. Like, for instance, you should... Do you have what you need? So, can I zoom in? Okay. Do you see a difference of perfect squares, and can you factor it? This is an Algebra 2 question. Actually, it probably takes us back to Algebra 1, but that, you know. What can we do with that? x minus 1 and x plus 1. That's something you should be able to do, right? I hope. Do you see that this right here is the same as this right here? Yes, I know, I'm about ready to blow your minds. I'm going to ask you to factor that. It's a difference of perfect squares. So instead of x minus 1 and x plus 1, what do you think it should say? Secant theta plus 1, secant theta minus 1. It's no different than the last question. It's just instead of x, we call it secant theta. But if you don't know how to factor, that's going to hurt. Because you won't know that you're dealing with tangent squared theta. Can you go backwards? Can you put these two things together using the good old FOIL properties we've taught you? Then you could go backwards and find that. So obviously, those are all things you should know, but they will be on your formula sheets. No sense in copying them down again. All right. Example 1. You're using the identities, not the triangles, okay? So no triangles. And yes, I can show you how to do it with triangles. In fact, you should be able to show me how to do this with right triangles. Which quadrant are we in? What information do we have? We've been told that the tangent is 5. That should narrow it down to quadrants 1 and 3, right? And then we have one other piece of information. So, what does that narrow it down to? Is it in 1 or 3? We're in quadrant 1 because we have a positive x value, right? So we know we're up here. What do you know about all the sines and cosines in that quadrant? They are all what? They're all positive. All your x's and y's are positive in that quadrant. If you're in a different quadrant, then you're going to have to think through it and say, okay, is that positive or negative there? It's important that you know which quadrant you're in. Okay, so let's see here. If the tangent of theta, that's the sine over the cosine, is 5 over 1. Can I make the assumption that the sine of theta is 5 and the cosine of theta is 1 and I walk away from the question? What's the highest sine value you can come up with in your brain? 1. So I can't make the assumption that sine is 5 and cosine is 1. I can't just say that. Now, what I'm about to do, folks, is I'm about to look at it from a slightly different perspective. We know that the sine of theta squared, or maybe we should just put the sine theta squared like you'll probably see in the book, plus cosine theta squared equals 1. If you do make this assumption, this would say 5 squared plus 1 squared. Do you guys know what 5 squared plus 1 squared is? It's 26, right? Clearly 26 and 1 are not the same number, right? What could you divide this side by so that you could make this turn into that? 26. But if you do it to that side, you better to do it to this side as well. All right, folks, start thinking. What's the sine of theta? The sine of theta is not 25 over 26. It is the square root of that, and give it to me. What is it? 5 over what? Not 26. Ah, the square root of 26. If you take the square root of the top, you better take the square root of the bottom. What would the cosine of theta be? 1 over radical 26. No, folks, I'm not going to make you rationalize those. I'm more interested in you understanding how that everything connects to the Pythagorean identity, what quadrant you're in, whether they're positive or negative. Now, the part that they didn't want you to do, right, it says no reference triangles. If you knew that the tangent of that angle was 5, then that would give you opposite over adjacent, wouldn't it? What would that make the hypotenuse? The square root of 26. And I do understand that you probably are, because we've done more stuff with triangles, you would say probably to me, why can't I just use the triangle? Yeah, I understand your point. So, you might use that as a backup plan, to help you. But you need to be able to use the Pythagorean identity to show me the work to get your answers. What's the relationship between A and B in this triangle? Angle A and angle B. What's so special about them? They're not necessarily 45 degrees, although if one was 45, the other one would be guaranteed to be 45. That's true, but I don't know what they are. They add up to 90? What do we call that? Complementary, right. Very nice to each other, They add up to 90. Now, speak radian. What do they add up to? Pi over 2. I know you don't like that, but there's a point to it. So A and B are complements. I know a test question on an SAT where if you knew that relationship, it was an easy answer to the question. If you didn't know that relationship, it made it more difficult, and you wasted a bunch of time. Solve this particular question for B. Solve that particular equation for letter B. B equals pi over 2 minus A. So this angle right here, I'm going to label it pi over 2 minus A. Maybe I should zoom in and make it fit inside the triangle. That'd be more cool. Hopefully I can. Pi over 2 minus A. I wonder if I can erase that little dot. It's annoying. Yes! I know. What is the, use the letters in the triangle that you see up there. What's the cosine of angle A? Cosine of angle A. Use the letters in the triangle that you see right there. X over R. Okay. What is the sine of pi over 2 minus A? Sine of pi over 2 minus A. Obviously, I'm now going from the other angle. That is also x over r. You're saying these two things are the same? Opposite over hypotenuse? Yes, they are the same. That was the question in the SAT question that I saw, was they gave me the sine of an angle and asked me for the cosine of the complement. I mean, they actually handed it to you and said, hey, the sine of this angle is 3/5. What's the cosine of the complement? If you knew, I mean, they actually asked cosine pi over 2 minus a. They gave me the answer, 3/5. If you knew that, it was a quick question, and we move on. You don't need to write any of that stuff down that you see on screen. Which one, the sine of angle A, where do you see that in the lower section for angle B? See how those match? What about tangent of y over x? Where does that show up for the other one? Cotangent, right? See, they match. What about the secant of angle A? Doesn't that go with the cosecant of angle B? So there's a matching one all the way through here. If you know SOHCAHTOA and CHOSHIKAO, I'm pretty sure you'll be okay. I don't know what. SOHCAHTOA, CHOSHIKAO? Okay. SOHCAHTOA. Change to a different color. CHOSHIKAO. You got your...
Can you say it again?
CHOSHIKAO? Okay, what is so funny about CHOSHIKAO? Remember your reciprocal trig functions. CHOSHIKAO.
I haven't seen that picture.
Oh, you haven't? Yeah, where? I didn't see it either. I gotta email somebody. I was upset. I was upset too, man. I didn't see it. Oh yeah?
You should ask for the picture.
Whoa.
Oh yeah, I wonder if it was.
And I'll never actually hear it.
Yes, it was.
Okay.
I remember.
All right. Moving on. All right, now. These are called cofunction identities. The one on the left is equal to the one on the right, so you can replace them. This is exactly what we just saw with the x's over r's and the r's over y's and blah, 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 blah. In fact, you and I just proved this one. I asked you what the cosine was of that angle, and you told me what it was, y over r, and then we went over to the sine of the complement, and you said that it was the same exact thing. So cosine goes with sine, cotangent goes with tangent, secant goes with cosecant. They're all duplicates, just as long as you understand the pairs. We should make up something dumb that goes with those. Right? I'll have to think about that. Make a song. I could. Okay. Okay, SC, that sounds like Santa Claus. Tangent, cotangent, secant, and cosecant. Oh, that'll be confusing. Ooh.
Santa Claus
Takes cookies from Mrs.
Santa Claus takes cookies and steals cookies.
Should we put a comma? Specifically sugar cookies. Takes cookies, comma, sugar cookies.
I like takes and steals.
It says takes and steals.
Takes cookies and steals cookies.
Okay.
Or no,
What about cakes? Cookies. Takes cookies and steals cakes. Whoa. Okay, maybe the Santa Claus that was in prison, but, he's reformed. Okay, folks, I need to know, remind me about my definition of an even function. Most of you are going to say something about reflection, symmetry, across what? If you're reflecting across the x-axis, folks, that means you're not a function because you failed the vertical line test. Oh, y-axis, yes. Okay. And then what we wrote down that you should remember, which many of you do not, is this definition. Okay? And I'll explain that or kind of review that with you here in a second, so it makes more sense. And then what about the odd functions? What was true about the odd functions? Rotation, symmetry, around what? Around the origin. Now, what did we mean by that? We could spin it 180 degrees and it had to look exactly the same. Don't be the kid that rotates it 360 because they always look the same. Yeah, I know. We got kids that do that. Well, if we spin it 360. Okay, now, the definition we had for that looked like this. Okay. Let me see if those of you who were with me remember this. Many of you were not, so you don't remember this. Okay. So we held our hands up like they were at the origin, and if you take a look at this, what do you notice about the x's for an even function? They're opposites, right? What do you notice about the y's? They're the same. And so we would say things like this: opposite x's produce the same y's. This is what's causing that reflection symmetry across the y-axis. Opposite x's, same y's. And if you could go down too, we could have functions that do this. But as long as the opposite x's produce the same y's, we had an even function. So if you look at this, what's it saying about the x's? They're opposite, but what's it say about the y's? They're also opposite. So we would do something like this. Opposite x's produce opposite y's. And you would get this kind of shape, where they were rotating 180 degrees. It would look exactly the same. But that was our definition that we talked about last semester. And I'm sorry if your teacher wasn't cool enough to show you with hand functions. Okay? Because the visual does help us. Yeah, they can be cool in other ways. Like temperature. Okay, how about cosine? Do we know how to graph cosine here? Let's change this to a 1, and we'll change that to a negative 1. Okay, do we remember how to graph this thing? And we got a cosine, right? What's the period of a cosine wave? 2 pi, right? And so we would do things like this. Right, and then we'd do the same thing on the other side. Stay with me, don't pack up. Even function or odd function. Even function or odd function. That is an even function, isn't it? Right? You could just basically fold it across the y-axis and it would look exactly the same. What about the secant? Well, we know that every time you crossed one of those x-axis points, you were going to get one of those asymptotes. Every odd integer multiple of, and then we could graph this and stay with me. Even function or odd function? You can fold it right on the x or the y-axis and it looks exactly the same. This is an even function. Well, would you look at that? If the cosine's even, so is its reciprocal function. I know. Now tomorrow, stay with me. Tomorrow we're going to look at these other ones. Do you have any feeling in your bones about whether sine is even or odd? It's odd because it goes through the origin. What do you think about tangent? Odd. It goes through the origin. Okay? And their reciprocal trig functions will also be odd. We'll talk about that and all this other cool stuff in our next installment of These Are the Days of Our